Now we are going to introduce a pretty new method to solve our one-to-one system with time variable demand, which we call continuum approximation method. So here, for demonstration convenience, we consider the case where the inventory waiting cost is much larger than the run cost, which is exactly the same as our shooting method. Recall a special case for time variable demand, that is, the demand rate is constant. It's a special case for the time variable demand. So let's consider the demand rate is d prime. And then recall in our one-to-one system special case for the inventory waiting cost is much larger than the run cost. We will focus on the triangle areas. So here we have one shipment. Definitely there will be more shipments later or sooner. This is a headway, and then this is a load. Then we have a fixed cost for the shipment. This area is S, and then the inventory waiting cost is CI. So in this case, the total cost for this one shipment, cost per shipment, should be the fixed cost plus the inventory waiting cost times this area. And then when we are given the demand rate and then the headway, we can calculate the area based on the triangle because we have this time horizon. So we will convert this cost per shipment to cost per unit time. Then we just need to divide the cost per shipment by the headway. So this gives us, okay. And then this is definitely a EOQ form. We can get the optimum headway given by the EOQ form. Yeah, you can double check this result with our one-to-one system with constant demand rate case. You may notice that there's a difference between the formula because we have a 2 in the factor, and that is due to we only consider the consumption side without considering the production side. We have introduced that in our previous discussion. Okay, so this is a special case when the demand rate is constant. So let's try to extend this idea for demand is not constant, but time varying. So in this case, it's a function over time. We still have the same parameters. So the most difficult part is how can we calculate the area? We have the formula for the area based on, let's see, this is T0. This is T1. We can have T0 to T1 and then integral on T1 minus T dt. So if you are familiar with the mean value theorem, a function can be estimated by this form. So that means we can always find some point in the middle which the gradient can estimate the gradient from any value t to T1. So you can see when the time varying demand rate does not change very fast, we can approximate this curved triangle into a typical triangle. So in that case, we can try to estimate this curved triangle into a typical triangle where the gradient here can be estimated based on some value inside. Okay, and then in this way, we can get the area as a triangle. So that means this triangle have a headway as T1 minus T0. So the total area for this triangle will be calculated based on some gradient in the middle between T0 to T1. So we can estimate the cost per shipment, CF, CI. Then we can write the cost per shipment into an integral form. So the integrand, actually this is a cost per time, which is constant. And after we take the integral, it's a cost per shipment. And then we can bring back the headway. So let's define the headway function inside this when t belongs to T0 to T1. So when we have t is between T0 to T1, the headway is just T1 minus T0, right? So we have this form. We can make some assumptions. So first, we assume that we have already estimated the curved triangle into a normal triangle, right? So we assume that this is what we call slow varying. That means the demand rate is slow varying. That means we can approximate the demand rate within a neighborhood by a constant value. Then in this case, we can estimate the demand rate just by the demand rate at point t, because it is slow varying, so the demand rate within t0 to t1, some certain value inside, can be estimated just by any dt. So in this case, the cost within this shipment can be written as a function with respect to t. So recall that we define the headway as a function, constant function within t. So this is just the cost per shipment, right? So we can further extend to total cost from t0 to tmax. We just extend the shipment, the integral domain, right? So there are multiple shipments from t0 to tmax. Then we can add them up together, right? So you can see we have t0 to t1, and then some integrand, plus t1 to t2, some integrand, plus until tmax btn t. And then interestingly, you find out the function or the integrand within the cost per shipment is just kind of a function with respect to t. So we can provide the uniform expression for the total cost by just using the integral from t0 to tmax with the function form. Okay, so note that here the definition for the headway need to be also extended, right? So previously for the shipment between t0 to t1, so the headway is a constant, t1 minus t0. So if we extend this to the entire planning horizon, then we can just have the expression for hst. So this will be a piecewise function, right? So t1 minus t0 for t in t0 to t1. And then be t2 minus t1 when t is the last shipment. So this gives us a step function, for example. So this one should be, for example, if we have t1 is here, t2 is here, then tmax is here. In the first piece, the function of hst should be t1 minus t0. And in the second piece, it should be t2 minus t1. In the third piece, it should be tmax minus t2. So this is a step function. And interestingly, you can see each of the step is a square, right? Because this is t1, t2 minus t1. And then the height, which is a headway function, is also t2 minus t1. So now we already have our total cost expression on t0 to tmax. Let's just look at this cost expression. So it's very interesting that it is a function with respect to t. Remember that the headway function hst is a step function. So the integrand is just a function at time t. So we want to do the minimization for this cost function. We can calculate the minimization for each integrand. Remember that our decision variable is the headway. So in other words, we want to make decisions on the headway function over t. Then this is pretty simple, right? For each value of t, we can just apply the EOQ form and we can get the optimum solution for each. We just derive it, right? So you can see that the optimum headway is determined by your demand rate. In the previous derivation for constant demand rate, the headway function is also a constant. But when the demand rate is time varying, your headway function is time varying. We should also note that this demand function is continuous, so our optimum headway function will be something continuous, right? So as the demand rate increase, your optimum headway function increase. As your demand decrease, your optimum headway function decrease. But as we assume in the beginning, like this headway function, actually what we really need is the step function for the headway. Remember our square sound like a step function, which are a combination of multiple squares. So the critical issue is that if we estimate an optimum headway function, so how can we find the corresponding step function? So because this is a square, because let's see t0, t1, the height, the step function headway is also t1 minus t0. So this is square. So we want to convert our optimum headway function into some squares. Yeah, after you determine all these squares, you can have this corresponding step functions. There are definitely multiple ways. So here we introduce one way to convert the optimum headway function into the step function. So suppose that we get our optimum headway function something like this form. Because we need to create multiple squares, so we draw a 45-degree line. And then we try to search one value on the vertical axis until some certain point. When we draw a horizontal line from this point, we can guarantee the area above this line and under this line are equal. Then we get the first point, P1. After we determine the first point, we will draw another 45-degree line and then find the intersection again, such that the area under this line and above this line are equal, and so on. Just keep doing the 45-degree line such that the area are equal. So we get this P3, and then we have the schedule based on this heuristic.